The topic of this video is rover mobility and locomotion. Hello, I am Swaroop from University of Würzburg, and I will be giving this video presentation, experiments or collect samples from another planets. We will need a transport system which can collect the samples and bring them back to the command station on the planet. The surface of another planets is really challenging, and we can't predict what we are going to face in the next 1 meter. So for that we will need a robust and reliable locomotion system for the rovers. So, how to design such a system which is capable of facing all the hurdles and bring the samples, or does it work effectively? Another question is how to design the mobility system of this rovers? Does these rovers have wheels or legs, or does it crawl on the surface? All the questions will be answered in this video. This video is divided into 4 sections. First one is introduction to the planetary rovers and their design requirements. Second one is about the wheeled vehicle rovers. Third one is articulated chassis rovers, and finally the fourth one is tracked vehicles. Let's start the video. First section gives the introduction to the planetary rovers, their design requirements and other fundamental characteristics. Generally, the locomotion systems have been classified into 5 classes. First one is wheels rolling. Second is tracks rolling. Third is legs walking. Fourth, body articulation crawling, and finally, non-contact locomotion. Now let's design a rover which has the same locomotion system like humus, that is with legs. Does that actually work? Let's see. The good thing with the legs is they are good in terrains and climbing obstacles. But their complexity and mechanical design and more power consumption makes them less desired for the rovers. So what is the solution for this problem now? The answer is using the wheels for the planetary rovers. Why? Because they are simple, ease of control, have advanced research already done, and reliable. So we decided to use the wheels for the locomotion system of the rovers. Next question will be how many wheels we have to use and which type of chassis have to design to overcome the terrain difficulties. We will see how the number of wheels are selected and also the type of chassis is designed. Best options is to use the kinematic linkages, which can improve the rover's obstacle negotiation capabilities. Generally rovers have 6 wheels. Why? Because 2 wheels are not so stable. 4 wheels requires more torque. 8 wheels are complex and consume more power. There are some main requirements for designing a rover. They are: number 1, forward and backward motion capability. Second, turning capability. Third, obstacle negotiation capability. Rover wheels are designed in such a way that they can climb, move on sandy, rocky and undefined planet surfaces. This is provided with the help of groovers that are designed on the rover wheels. The shape and angle of these groovers depends on the type of mission of the rover. Till now we saw some introduction concepts about the rover locomotion systems. Now in this second section we will see in detail about the mechanisms used in the wheeled vehicles, and in particular about the rocker bogie mechanism and how does it work. Also we will see the rovers which implemented this mechanism and other types of rovers which uses the types of this locomotion system chassis. Complexity of the locomotion mechanism is a trade-off between the mechanical complexity and obstacle negotiation capability. Let's see in detail about the rocker bogie chassis mechanism. It is a US 6-wheeled chassis which is a cab settled on the kinematic lever linkage, which is the US standard planetary mobility system. The rocker bogie mechanism has been used in many US rovers, namely US Sojourner Mars Exploration rovers and Curiosity. Here you can see the animation of a rocker bogie mechanism. This mechanism doesn't have springs because the springs provide an upward motion when the rover is climbing an obstacle, and this upward motion reduces the traction of the other wheels. So that is why the springs are avoided in the mechanism. It has a rocker and a bogie where the front end of each rocker are directly connected to the wheels. The rear wheels are connected to the bogie link. The bogie joint was limited to plus or minus 30 degrees. In the figure, the rocker is the front one and the rear end is the bogie. There is a torsion bar which ensures that the 2 rockers' joint angles are equal and opposite with respect to the rover body. All the 6 wheels are driven independently and attached to an articulated frame, whereas the 4 corner wheels are independent to provide double Ackermann steering. Now we will see a micro rover called Kopvik which used this rocker bogie mechanism. This rover was developed by the Charlton University, which has 0.782 meter width and 0.5 meter length. The wheel radius of this rover is 75 mm, and in width of wheel is 70 mm. This rover wheels has grousers with 5 mm, high and our helical angle of 19.4 degree. The rockers of this rover are kept at angle of plus or minus 16 degree. All the wheels on top uses force sensors to maintain the traction of the wheels all the time. There was some research showing that the rocker bogie performance might be increased if some of the linkages integrated are in order. Also, the stability of the mechanism can be improved by using onboard controllers. Therefore, there are other types of mechanisms which try to overcome the disadvantages of the wheeled vehicles. Some of them are mentioned here. Japanese lunar micro rover Micro 5 has 5 wheels out of 4 lie at the corners and the last one lies beneath the center point, giving the climbing robustness. This rover from École Polytechnique Fédérale de Lausanne has 6 independently actuated wheels and a 4-bar rhombic linkage integration. In this configuration, the front wheel is fused on a spring-loaded fork and the rear wheel is attached diagonally to the rover chassis with 2 bogies on each side of the rover. The bogies can rotate freely with a pivot. The front wheel is attached in a parallelogram-shaped linkages which has spring suspension. This helps to remain the ground contact of rover and to change the angle of the front wheel in case of any obstacles. When there is an obstacle and the front wheel stores the energy and uses it to terrace the obstacle. Solivero's design enables it to climb obstacles twice its wheel diameter and enables slope negotiation of 40 degrees. RCL-C series. Simpler than D series. Suffers from suspension lever hang-up problem. RCL-D series. It has one more extra lever which provides mass overhead. RCL-E series. Longitudinal asymmetric design. Unlike rocker bogie mechanism, the rear wheels are not connected to front wheels. Near vertical wheel movement. Can easily negotiate the obstacles. Drawback: suffers from poor static stability on high slopes. To summarize the first section, we learned about the benefits of using wheels for the rovers and detailed working mechanism of the rocker bogie mechanism and the rovers which are using that mechanism. Also, we saw some other models which are the new varieties of rocker bogie mechanism. Now in the next section we will see what are the articulated chassis and how does that work and which rovers implemented this mechanism. Third section in this video is about the articulated chassis rovers. In this section we will see the articulated chassis design of the 3 rovers, namely Marsohode, Nomad and the Sample Return Rover. The articulated chassis models have been extensively developed but haven't used in any real rover. First let's see about the Marsohode rover. Its chassis is 1.5 meter by 1 meter with a mass 35 kilograms. Total vehicle mass 100 kilogram. Wheel dia 35 centimeters 70 centimeters width. Able to negotiate obstacles twice its wheel diameter. Max velocity 0.02 km per hour. Power consumption 25.3 km. It has been used to develop the chassis of Planetary Rovers. The state of art of this rover, the 3 articulated units and the design of the wheels. Here the articulation is used in between the cab segments which actually increases the mechanical complexity. Generally the articulated chassis helps the rover wheel to climb inclined surfaces. Marsohode has an integrated chassis in the core design which has a torsional spine. This rover has a nice optimal traction provided by the multiple cab assembly and the drum-like shape of the wheels. It has 3 cabs or axles which are coupled to the 2 actuated rotational joints to take advantage of the flexible spine between those axles. The cylindrical tapered wheels has the volume which can be used to store hardware and also the batteries, which in fact lowers the center of gravity of the vehicle. The design of these wheels is made such a way that the chassis won't get stuck when climbing the obstacles. This rover is capable of climbing high-angled slopes with the help of levers which are attached to the rear wheels. There is a possibility to increase the capability of slope climbing, but also there will be a problem of backsliding. There is another type of Marsohode rover which uses multiple case with rotational degrees of freedom. The disadvantage of this rover is its weight. For Russia's 2001 Mars mission, Marsohode has been selected. The primary objective of this mission was to carry a payload. This mission was later cancelled due to some other reasons. The challenge in this mission is to integrate the payload to the articulated segments of the rover. This problem could be avoided by using the multiple body varying degree of freedom articulation. Also, this will be a great design that helps in climbing or negotiating the obstacles. There are other rovers like Marsohode which use the articulated mechanism. The next example is the Nomad rover. The main mission of this rover is to find the meteorite in Antarctica. This rover can change its ground footprint by using the 4 linkages and expanding or contracting the chassis. This mechanism helps the rover to negotiate the obstacles effectively. The main advantage of this mechanism is the very less probability of getting stuck in the obstacles. Nomad uses explicit steering mechanism which actually turns the wheels of the rover when the chassis is expanded or contracted. This in fact reduces the power consumption of the rover. The third type of the articulated chassis rover is the sample return rover. This rover has 4 wheels with variable ground footprint. This rover is designed to collect the samples on another planets and bring them to the Earth return vehicle. Till now we saw what is meant by articulated chassis and the types of rovers using this mechanism. In the next section we will see the rovers which uses another type of locomotion system rather than using wheels. In this final section we will learn about the tracked wheeled vehicles. Let's dive into it. When we have wheeled vehicles, why do we need tracked vehicles? The answer is the tracks support terrain contour which makes them reliable for off-road applications. This is because of their high ground contact area and high traction on ground. Also they generate amazing drawbar pull force compared to all-wheeled vehicles. But the only disadvantage of these vehicles is they consume more power. They usually comprise of tread, diver sprocket, idler wheel and bogie wheels. The rear unpowered wheels support the track and reduce peak ground pressure. Another advantage of tracked vehicles over wheeled vehicles is they do not suffer hang-up failure, which is a common issue in the wheeled vehicles. The tracked vehicles are mechanically inefficient because of their higher track-to-ground friction. There is a torsion bar, arm, inclined spring-based shock absorber and bump stops in the tracked vehicles. There are 2 types of track drive system. First one is friction drive and the second one is positive track drive. Friction drive relies on the friction between drive wheel and inner surface of the track. The positive track drive relies on the sprocket teeth to the teeth on the inner surface of the track. Let's see some example rovers which uses these tracked wheels. First, Urban. The second rover has small robotic arm on the front which can be used to climb. Second, NASA's tracked racer has similar design like the Urban the second rover, but instead of arms it has a bucket to dig the soil. Third, a 3.2 kg nanocod uses a foil track wound around its wheels on the locomotion system. To maintain the horizontal direction of the chassis, the whole track will be rotated 90 degrees. Nanocod has a speed of 5 meters per hour and it is able to negotiate the obstacles up to 10 centimeters height. There is no need of bogie wheels and hydraulic dampers for a nanocod rover. Because of this, the maximum ground contact area cannot be maintained over the rough surfaces. New Elastic Loop Mobility System (ELMS). This system can favor high mobility adequacy. Now let's have a look into ELMS and how does it work. This mechanism eliminated the problems that are in the traditional tracked vehicles such as high internal friction, mechanical complexity and link breakage problems. This system has 2 end wheels, namely drive wheel and idler wheel. There is a continuous band which is wound around these 2 wheels. The good thing in this system is there are no bogie wheels. So that means no internal friction losses. You might be wondering, how does this track say like that? It is because of the performed longitudinal and transverse curvature of the band. The band is a highly elastic metal band. This curls over its width so that the sections between end wheels are flat and trout, which was caused by transverse curvature. This highly elastic metal band is usually made from titanium alloy. The track acts as spring suspension which raises the wheels and vehicle, and it ensures that rocks and soil fall from track before they got jammed into the wheels. This band's elasticity is highly rigid and makes sure that there is no need of bogie wheels, which in fact reduces the power requirement of e-vehicle. That's the reason the ELMS is more power efficient than the traditional tracked vehicles. This system had been implemented in Viking 3 Martian mission which got concealed later, so this mechanism never flew. As mentioned earlier, Kopvik rover is designed to accommodate different types of chassis designs. Now ELMS is a preferred track solution. The chassis changing to Kopvik rover is very easy. It takes like 5 minutes to change from wheels to the tracks. The only problem that ELMS encounters is the dust, rock mitigation. This brings us to the end of this video. To summarize this video, we saw the introduction of rovers and different types. Next we learned about the wheeled vehicles. Later we saw the rovers using articulated chassis and their types. Finally we saw the advantages and types of tracked vehicles. Thanks a lot for watching this video. The references are published in the script.